When we were talking about Lewis structures, we have been drawing the molecule on paper without caring too much about what is the actual shape of that specific molecule. And that's what we are going to talk about now. After we have learned how the electrons and bonds are distributed in a molecule, drawing the Lewis structure, now the next question is, how are these different atoms placed in the three directions of the space, in the 3D? Well, the principle that we will apply is that we will try to minimize the repulsions and maximize the space. This theory is called the VSEPR, that stands for Valence Shell Electron Pair Repulsion Theory. The basic principle is to identify a central atom, and then, which usually is the least electronegative, will go in the center, and place the surrounding atoms as far away from each other as possible. Okay, and sometimes we will see that these surrounding atoms are actually lone pairs, but the idea is to place the surrounding atoms or surrounding lone pairs as far away from each other so that they minimize the repulsions. Okay, so let's see if we can figure out some simple structures just by looking at the Lewis structure. So in this case, let's say that we want to draw the Lewis structure of these three different compounds, and we will apply the principles that we just said. So identify the central atom, draw the Lewis structure, and come up with what is the orientation of the surrounding atoms in the space. So if we start with beryllium fluoride, beryllium is the least electronegative, so we will go in the middle, and two fluorines. Beryllium only has two valence electrons, so it can only form two bonds. So notice that this would be the Lewis structure of beryllium fluoride. If we try to place this in the 3D, well, in the three dimensions, this will form a line, because there is nothing. The best way to keep the two fluorides away from each other is forming a line. This is a so-called linear structure, and it's characteristic to have a 180 degrees if you think of the central atom as the hinge. Okay, so this is one of the most simple structures when you have at least three atoms. The next one, sulfur oxide. You may see, depending on the textbook, you may see different representations of sulfur oxide. We will not dwell too much into it. You can draw maximizing the number of bonds. Some authors will say that there's no way that sulfur can make so many double bonds. So another extreme, because of the difference in electronegativity, you could actually draw it like that with a lot of separation of charges, but still, and of course sulfur does not need to follow the octet rule. Both of them in this course we will consider them valid. Of course, at the end is a combination of the different resonance structures with different weights. We will not discuss it, but what's important now is that in both representations the three oxygens around them is equivalent, and they will try to stay as far away from each other as possible. So that means that these three oxygens will stay on a plane, and this structure is called trigonal planar. Trigonal planar means that the four atoms will be on the same plane, and the angle oxygen sulfur, there's not a, sorry, maybe I shouldn't, whoops, I shouldn't be, I'm erasing more than what I want. All right. The angle here is 120 degrees. Of course, 120, 120, and 120 is 360. That would be the whole circumference. Okay, and the last case would be methane. I'm sure that you are familiar with the structure of methane, and hopefully you are also familiar with these symbols, a way to represent the bond. That means when it's solid, it's coming out of the screen. When it's dashed, it's going into the screen. What's important here is that this is a tetrahedron. A tetrahedron has a characteristic angle of 109.4 degrees. Okay, so just when you have two surrounding atoms, you have a linear structure. When you have three surrounding atoms, you have a trigonal planar. When you have four surrounding atoms, you have a tetrahedron. Okay, so that's pretty much what you may have here in nicer pictures, but that's what we have said. And you have a lot of examples for you to practice. Make sure that you can draw the Lewis structure and realize that in all these cases, for the linear, that you actually see a linear, so it's important that the central atom has no lone pairs. For the trigonal planar, the three atoms have to be the same, have to be equivalent to be a perfect trigonal planar structure. And for the tetrahedron, tetrahedron is the name, the adjective is tetrahedral. Also the four atoms have to be the same. The four surrounding atoms have to be equivalent to have a perfect tetrahedron. I think I said 109.4, maybe it's 109.5, I apologize. It's around that number. But it's perfect, and it's all the angles of the tetrahedron are 109.5. Okay, the same way that this is 120 degrees and 120 degrees. All right. When you have 5 and 6 surrounding atoms, it's less common, but still you may have seen it before. When you have 5 surrounding atoms, like phosphorus fluoride, it's a little trickier because suddenly now you have the 5 positions are divided in two categories. The ones that are in the middle here, they are called equatorial positions, and they are away from each other 120 degrees. 120, as this number says here. However, notice that these positions, these two positions, are called axial. These positions are called axial. It's important to understand that equatorial, and we will talk about that, atoms in equatorial position have less repulsion because they have two atoms at 90 degrees and two more at 120, and positions, atoms in actual position will have more repulsion because they interact with their neighbors. There it has three different atoms, and at this point you may not see, I've been writing too much on this figure, but it has three neighbor surrounding atoms at 90 degrees. So it's closer to have three neighbors at 90 degrees than to have, like in equatorial position, two neighbors at 90 degrees and two at 120. So it's important because in the trigonal bipyramidal structure, the 5 surrounding atoms are not in equivalent positions. That's the only case of the 5 cases that we have talked about. Finally, the sulfur fluoride, you have 6 surrounding atoms, and in this case you have a perfect octahedron. All the atoms are at 90 degrees from each other, and all the 6 surrounding atoms are equivalent. Think about it. If you rotate this, there's no way to distinguish one from the other. Okay, we'll practice more.